Hey, everybody. Thank you very much for that intro, Ron. OK, well, thanks for being here. I'm excited to tell you a little bit about our lab and what we do. But the SSL has had a long history dating back to the 90s when I was a student there. So I started out as a master's student there in 1998-ish. And now, apparently, I'm directing it. So we've got a lot, and I'm going to give you a little bit of a history, but I'm going to try to touch on the things that we're doing now and going into the future a bit. OK, so first I'll start with basically who we are, because I think, I think that's what makes the lab, right? So here's our leadership team. So I am now the director. We also have Dr. Alvar Sanzo-Tero, who was the director before me, and then, of course, Professor David Miller, who started the lab, and he was, my advisor in '98, and probably also worked with Ron. I think you were there during the time that I was gone, that little 6-year hiatus.
They gave me my first year off. That's how I got
started. There you go. Yep.
So we go way back.
Right now, we've got 6 students at the doctoral level and 4 that are some master students. And then we have a number of undergraduates. So that was a great segue there. Basically, UROPs who come in and out of the lab and work with us for a term, like an IEP, a summer, et cetera. And many of them will sometimes then become the visit students who stay with us and actually do their graduate work. I also wanted to mention that our sibling lab is the ARC lab. So Professor Richard Linares, who spoke at this in April, who does astrodynamics and orbital dynamics and robotics. He also works with us, and his students sit with us and also collaborate with us. He was the formal co-director with me until just a couple of months ago. And finally, we're also in the middle of doing a small, we're trying to take all of the groups in the department that do work in space, especially hardware, and sort of put them not into one lab, but into one sort of collaboration, where we're sharing facilities, we're sharing proposals, we're sort of working with each other in a more formal way. And so there's some information on our website right now about that. It's sort of in the early stages, but these are the labs that are mostly active in it. And I think you're going to hear from Professor Cordero a little bit shortly after me. So that's just an overview of who we are and who we work with. This is a slide that you're going to see multiple times during the talk, so you don't have to get it all right now. But basically, what I wanted to try to get across here is that what we do at SSL is we start with analyzing mission architectures and seeing what the technologies are that are needed to really push the next big space telescope. And then we will identify those key technologies and work them in the lab, in the prototyping stages. And then eventually, we actually try to get that we're doing actually on orbit, and we've had some success doing that. So we're sort of going through the entire life cycle of space, and I do have one student who actually did exactly that. He started on the napkin, and he actually got to operate his instrument in space. So that can happen. Not necessarily everyone, but it does happen. So on the first line here, you've got the kind of architectural studies that we're looking at: multi-objective optimizations. How do you design a telescope that has what are the factors, how do you balance the controls and the structures, or the thermal and the structures, to get the pointing that you need for something like the James Webb? So astrodynamics and constellation design. This is Richard's work, where you're looking at where to basically slot in the payloads in these large swarms. Then if you go down to the next line, we're talking about the technology development. So there are the test beds we have in the lab. We have test beds for telescopes. We've looked at how to move things next to each other using only EM instead of having to use actual propulsion, or chemical propulsion. And just recently, like everybody else, we're looking at, of course, the CubeSat revolution has sort of gotten us to be able to put things in space a little bit easier and try something out at a little bit, lower cost. And then finally, you've got the on-orbit, work we've had, and I will discuss each of these in a slide, so I'm not going to go into them here, but just gives you hopefully the overview of what the lab is doing, or what we like to, how we focus. We're also very, because we're a lab that is part of the academic department, we are a key part of the STEM education that students are getting. And so this graphic kind of shows the three parts of that work with each other. So there's the SSL, where the students are, and the researchers. There is it is the conceive, design, implement, and operate, which actually Dave Miller was one of the people who started that at MIT. It's now run mostly by Professor Cahoy and Ali Devek sometimes as well. But these are hands-on, multi-semester capstone for the courses. And for many years, and even still, the projects in SSL will be featured in this, here, and that's sort of the start of the idea. That's where we get to the beginning, where the prototyping, would happen here. And then there's our space, the community, our scientists and PIs that we work with. And over on the left, you'll see. Sort of the places that we're working with, the MIT Haystack and Kavli Institute, to NASA and the University of Arizona, and of course Lincoln, which you see, you'll see Lincoln Lab pretty much everywhere on here because they're a close partner of ours. So this, I like this, the plot, because it just sort of gives you an idea of how these things work together and what the students are experiencing through each of these different combinations. The next slide is just a quick overview of what the capstone has looked like over the years. You'll see that it only goes to 2012, so slide probably needs a little bit of updating, but it's really hard to fit all the things on one, and I like this because it just gives you an idea of where we started and where we're going, or like what we've done over the years. So Spheres was one of the first capstones. It was eventually became a national laboratory that was on actually ISS. It just came down in 2021, so it's been operating for a long time. Then there was EMFF, which was looking at spheres, but instead of having thrusters to move them, you would use basically EM forces to move them. And that actually did also go on the ISS in the shape of these rings that went around the spheres. There was a couple, I don't actually know Moretta very well. So Castor was going to, I think, a propulsion, so lunar type of work. Going to skip down to Exo. That's a planet. That actually launched recently by JPL under a different name, but it started at SSL. And in fact, a number of students in this picture went to work there and are who actually got the CubeSat in space. And that was a CubeSat that was looking for Earth, so kind of like the test approach doing photometry, but the idea is instead of doing an all sky, like looking at the whole sky, you would have a whole bunch of these like little CubeSats, each staring at a star. So you could integrate for a long, you could integrate for a while and not miss any of the events that cause the light to dim. And that was actually a really successful spacecraft, and it started here as well. And if I continued this on, so Rexus, which you'll hear about, was also one of the capstones that actually made it to space and went to visit the near-Earth asteroid. This just gives you the same kind of things I've been saying, but in a different sort of graphic, and I like the life cycle idea. And I think the important part that I want to mention here is I like to think that SSL kind of lives in the valley of death here, where you've got these technologies that you can get them to work on the ground, and then you try to put them in a space, and there's this sort of gap between getting it there and then getting it actually on orbit, and that's the part that I find really fun. And so by being a part of this entire life cycle, it enables us to get that on-orbit experience and to inform what's going to happen for the next time when we go back to the beginning and we're working on the next big idea. It also, I think, is great for our students who get to kind of see this. And like I said, I do have one that started at the beginning and went all the way to the end. Sometimes, a master, he was here for 10 years, so sometimes the master students will, be in sort of one part of the life cycle. He's one of those that liked it so much that he decided to stay and finish it off. But I really, really think that the hands-on experience that the students are getting in SSL is hugely valuable. I have a couple of students. I have one student who operated one of our instruments with me and then went off to work on the Mars, on the Mars cameras. And she wrote to me the first day. She's like, "They're shocked at how much I know about operations." And I was like, "That's awesome." So you really get this nice hands-on experience, which is just so great. Okay, so I'm going to go back to this chart, and now I'm going to talk about a couple of things in each of these three areas here to give you a flavor of the projects that we're doing. So we'll start with the architectural analysis and trades. So these are just some examples of the kind of questions we might ask. So planet finding interferometers were a big thing in the 90s. It's not so much. People now are looking at chronographs and different ways of doing it. But then we were looking at for how many, what's it going to cost, and how many images can we get for the architectures of one of these interferometers. And you might be trading lots of variables there: the number of spacecraft, the kind of the propulsion, how you're doing. I get the formation. I think for this one, this was not a structurally connected. It was separate spacecraft that were flying together. Then there's modular segmented telescopes. A lot of our work, you'll see, is sort of focused on how do we get bigger telescopes in space, because there's an issue with basically how much mass that you can launch, and there's also an issue with how you can store it in the launch vehicle. So having to deploy a telescope once you get to space is not easy. Anybody who's followed so James Webb will know that it costs a lot of money and it takes a lot of time. I was working on that in the 90s, and it's hopefully going to launch soon. Another thing we're looking at is sort of reconfigurable constellations. And if you've got a constellation of satellites up there and you want to look at something else, you could launch some more satellites, or you could reconfigure the ones you have to do that. So it's a way to kind of look at using the assets we have as opposed to adding some more, which is expensive and also adds a lot to an already kind of overcrowded space. Another aspect of sort of the early design, or just a thing that maybe encompasses all of what we do, is model-based systems engineering. I'm not a researcher who's looking at how to do that. There's a lot of system models and ontologies and ways that they talk to each other. I've heard MBSE. That there's analogy to CAD, right? That before we had CAD, everyone was sort of drafting in their own table, and then we had CAD, and it changed things. And I know there are some that think that MBSE can can do that. And I think the way that I find it really interesting and useful is it allows us to get the system engineer out from behind the spreadsheet. I've worked with many science PIs who are sort of like, systems engineering, it's just checking off requirements. And it's totally not that. It's super important, and you need it for these systems to actually succeed. And I think that you can sort of bridge this gap between engineers and scientists if you have these models that you can actively change and work as you're talking about things. Otherwise, we're both coming at it with very, very different languages. So if you can imagine if computational power was infinite and free, you could basically design at the speed of thought. I mean, that's kind of going out a ways, but right now it's just how can we better design our systems using some models instead of spreadsheets and static documents. One of my students, this is actually the one that stayed for 10 years and did Rexus. He looked at, as you're going through the design cycle, things are constantly changing, or they're often changing. Can you feed that back into the system, into the model you have of your system, and help it tell you what to do with the new information, which is super useful if you've ever tried to run one of these programs. Going back to the main slide now, I'll talk about some of the projects that are basically developing the technology here that haven't actually flown yet. And a lot of them we're trying to get there. So I'm going to start with this picture. This is actually an older project. But first of all, it's beautiful. So the student who did this was also an artist, and she's amazing. Anyway, but the idea here, this is, looks like the James Webb, perhaps, if you're familiar with that. And the idea is here, instead of having structure that connect the James Webb, can we use, EM to just hold everything, together, and to actually simplify the deployment. So the James Webb has, a sunshade that you have to deploy out, like the layers of it. Could we do that, electromagnetically instead of having structure that does that? If you've ever tried to deploy something in space, and I think your next speaker is going to talk about antenna deployments, and it's hard. And the mechanical engineering that goes with that, it's tricky. And so if you can get rid of some of that structure, what does that enable? So Gwen looked at that, and this is certainly something that this project is not currently active, but something that we think about every time we're looking at a new project is how to make these apertures without having to structurally connect them. a project that I am working on right now is a strip aperture telescope. Again, in that sort of theme of the farther you can see and the better you can see goes with how large your mirror is, right? But getting that mirror up in space is tricky. So the idea behind a strip aperture is that instead of having a full, circular aperture, you can have 2 rectangles that you then spin. And by doing that, you can actually synthesize the full. You can actually synthesize the image. So the COI that we work with for this is out at that's a PL, and I have a couple of students working on it as well. This actually started in one of the capstone courses a couple of years ago. We asked the students to basically build a what we're trying to see is, as we're spinning, are we able to slew the spacecraft and track? You can imagine if we're looking towards the Earth, we have to slew it to keep it above whatever we're looking at. Can we do that while we're spinning? Is that a dynamics and controls the problem that's manageable? So the students we're actually building hardware to test that. They got pretty far, and now it's in the hand of the grad students who are taking it from their sort of concept to reality. And so here's a picture right now. We have all of the sensors and actuators on a bench, and they're all talking to each other. They're using the robotic operating. We use ROS to have all of the actuators and sensors communicate. We've got a test bed that is looking at the IMU and our camera that is telling us where we are to correct for the drift in the IMU. And all of these pieces are being worked separately. And in January, we're going to basically put them back up on the test bed where we can spin it and slew it and actually test out the control algorithms. So this is it's a good example of something starting in the capstone class and moving ahead. And now we're looking for ways to get this in space. We're hoping to put it on a CubeSat where we have some proposals out to do that. So WaferSat is another example of this one. This is started as a Europe project, actually. So Dave Miller started this, and now I'm running it with the students. The PI is they're from Lincoln, and they are looking at, when you print your CCD camera, right? You're printing it all on a wafer, a silicon wafer. You're using like MEMS technology. So instead of just printing the camera part, let's print the entire thing, the whole satellite. And the exciting thing here is, one, you can get much, much smaller, right? So your mass goes down. You could launch a whole bunch of these in one sort of container. But secondly, a lot of the cost, people always say that CubeSats are so much cheaper, and they are, but they still have to be tested, they still have to be integrated, and that's really expensive. And so I feel like, and so sometimes what happens, in my opinion, is that part gets skipped over a little bit, or there's not enough money to do it properly, and then you have CubeSats that don't quite get where they're trying to go. So WaferSat would be nice, because you'd kind of get rid of all that touch engineering that is needed to put things together. So Lincoln came to us and they said, hey, we've got the MEMS technology. We wanted to make this happen. And Dave put together a group of Europs and had them look for what are the parts that you'd want to put in there. What commercial off-the-shelf stuff can we sort of get into the wafer to make a satellite work. Since then, I've got 2 students on it. Like now, one of them is looking at the thermal. One of the challenges here is there's just not a lot of mass, right? That's the good thing, but so thermally also the bad thing. Because when you're going in and out of the eclipse, you're going to heat and cool really quickly. And so this is something that the folks who started this weren't really thinking about, because and so we sort of brought this in and said, we're going to start looking at how to design this. It's a highly coupled system. When you have a satellite that is bigger, you can put like a heat strap and sort of dump your stuff off the radiator. It's away from the heat source, et cetera. For a WaferSat, you can't do it. It's all right there. And so figuring out how to use coatings in sort of novel ways, maybe even like the orientation of the satellite. What are the knobs that we can determine? We looked at using actually phase change material to take up some of the energy. So when you go from eclipse to daylight, you don't go as quickly, because some of that's going into the change of the phase of the material. So yeah, it's really, really fun. It's a super interesting theater project. Oh, and my other student is testing the batteries, looking at how they operate thermally at different temperatures, and that's also going to inform the thermal design. So we've got a couple of things. Oh, and the last thing, I could talk about this all day. It's got the spray. So the propulsion for this is actually done by the Space Propulsion Laboratory, so Professor Lozano, and he's actually etching the nozzles of the propulsion into the wafer. It's super cool. I'm kind of jealous. I like that part of the project, but so I also have a student who's going to actually test the propulsion units at different kinds of, so in the vacuum chamber to see what the performance is given a lot of temperatures. So Lincoln is really serious about this. We're hoping it launches, and we're excited to have a little bit of theater role in it. Okay, now I'm talking about the on-orbit stuff. I'm doing okay-ish. So Mode in Maze is where this all started. This goes back to 1998, and I can't give a talk about SSL and not mention them. This was Dave's work. It was the control structures work, where we're looking at how the structural basic behavior of a system impacts the ability to control it. These were experiments that went up in the bay of the orbiter and eventually onto ISS. And the box right there sits on my desk now. I need to get it to the museum. Spheres is a laboratory that, as I mentioned, started in 1999 as part of the capstone, and just came down in 2021. So there's a lot of years of history here. It was on the ISS. What they are these tiny, soccer ball-sized satellites. You can think about the scene from Star Wars where Luke Skywalker has the little drone. That's what they are. That's how they started, and that's what Dave said. Said to the undergrads. And now what they're used for is to look at control algorithms to sort of to fly things near each other. If you're trying to synthesize an aperture, if you're trying to do docking, if you're trying to give something fuel, etc. Spheres, like that's a test bed where you can look at all those kinds of issues. It's you get the 6 degrees of freedom. And you also get like a large sustained fit time where you're in actually microgravity, which you can't do on Earth. So the idea is, if you can't get the space environment in your laboratory, bring your laboratory up to space, and that's what Spheres is and was. It now has been replaced by Astrobee, which is out of Ames. So it's sort of started something that is going to continue. I guess I'll say that. The other thing about Spheres is, it was used, and this is continuing too, but with Astrobee, used to run a STEM outreach, where students from middle schools and high schools were able to compete, trying to write algorithms to control the spheres. There'd be a game they had to play, like Mine an Asteroid or whatever, and the 2 teams that made it all the way to the end got to see their code run on the spheres on the ISS. So Alvar actually ran this for many years. It's an amazing success. It's there's a documentary about it right now, and it's a really wonderful watch if you get the opportunity. Okay, and then small theta flight systems. So I did my original work in the lab in the days of like the control structure stuff and the space, sim and James Webb. And then I left, and then I came back right around the time that we were starting into the CubeSat world. So what I'm going to talk about with my remaining 5 minutes is a project, Rexus, which was a student instrument that was on the OSIRIS-REx spacecraft. So that launched in 2015, got to the asteroid. It's now on its way home with a sample of the asteroid. So Rexus had no part in the sampling, but what we did do was look at the asteroid in the X-rays. So we were staring at the asteroid while we were orbiting it, and looking at the X-rays that came off of it, and trying to tell what the asteroid is actually made out of. What are the what's in the regolith. So the R stands because we're target. So we target the regolith. We're looking at X-rays. We're doing imaging using a mask that allows us to say not only what the spectral content is of the X-rays, but where they're coming from on the asteroid. And then it's a spectrometer. So Rexus. This is where Rexus started in the SSL in 2011, and this is where it ended up in 2015. So I like this little idea of we had an idea, and we actually got on the spacecraft and went to the asteroid. This is just sort of a timeline of how we made that happen and how the students were involved. And this chart here shows you the number of students. We had over 80 students that were involved. So each of these lines is a student, and the length of the line will tell you how long they were here. So this is Mark, who was there from the beginning to the end. But there were others that were, that sort of spent a long time with us as well. So did PhDs, get masters on this, and it's color coded to show you where they are, like now. So where did they go after they left, their experience with with the instrument. So I could talk about this instrument. It's my baby for literally as long as you guys would like to listen to me. So I'm not going to go into it much further, but I do think it's a great example of what the SSL wants to do and sort of get our students involved. There was some technology, the development on this too. The CCDs had a filter on them to block the optical, because of course we're looking at the asteroid. We're getting like light from the asteroid as well, and also X-rays. And we only want to see X-rays. We don't want to see optical light. So we had to put something on there to stop that. It's a filter that is actually deposited on the CCDs. It's not a standalone. So Lincoln, did that. This was the first test. It's been done before, but not in the soft X-rays. So not where we were looking. And in Rexus, I would say it was a success. We got on the spacecraft. We got out to the asteroid. It operated. The sun did not cooperate, so we didn't actually get to see what the asteroid was made of, which is a little bit disappointing after how long it took us to get there. But from a student project, it was a huge success. I don't think anyone thought we were going to make it even on the spacecraft. So, we actually were able to image an X-ray. A transient that was off the limb of the asteroid. So we did get some scientific observations from it, just not the ones that we were hoping to get. I think I'm done with my time, so I'm going to wrap up, but thank you.
So we do have time for a couple of questions. Let's do this in parallel. Why don't we change the computers over for the next speaker at the same time? If anybody has a question for Dr. Masterson, otherwise I'll ask all my questions.
Thanks very much, Rebecca. So I'm a colleague of Ron's, and I would say I have a number of companies that I work with. I think that would love to get involved. So part of this is how do they do that? What's the easiest way or the best way?
Yeah, I guess you can send them to me, or we can have a conversation. If they want to get involved in terms of the small sat, the center that has multiple labs, I can give you contact information for that in particular. But both of those would be good avenues.
Does it tend to be, I'll let somebody else ask the question, but does it tend to be sponsored research, or is it's more of a collaborative event, or? The Small Sat Center research, or? Sort of, I guess. Yeah, all of this is mostly, so what you saw here was all sponsored, either from NASA, so WaferSat, so Lincoln Lab, funds that internally and funds us to do the part that we do. But for the Small Sat Center, we are looking for industry partners who would be interested in getting involved in some of this work, because we want to have a center that is able to be sustained. Right now, you kind of go on the project cycle. You've got some money, you do some stuff, and then you kind of wait until the next. You know what I mean? And so having a more sustainable center with an industry partner would certainly be of interest. Okay, thank you.
Yeah, sure.
Any other questions before we move on? I have one,
Sure.
Rebecca, which is, obviously you've seeded a lot of students into NASA. JPL features prominently. Are you seeing students starting to go into private commercial startup kind of space, like Blair's company, Lunar Station?
Yeah, we certainly have students going to SpaceX, to Blue Origin. A couple of Rexus students went there. So Axion, which is a company that came out of the Space Propulsion Laboratory, is another one. And then there's a couple of smaller satellite. We actually, one of my students this year, interned at Astra, which is a startup, rocket company. Right. So, and the students definitely have interest here as well. They definitely love going to JPL and doing the Mars stuff, but it's a lot of interest in the small.